Hello, good morning. I am Sunandan Chakraborty. I am an assistant professor in data science at the IU School of Informatics and Computing. Today I'll be talking about one of my ongoing work, which is about exploring dynamism of causal relationships extracting from the text. This whole work started with a very interesting observation that in India, onion is a very important crop, and over the past few years, it has shown amazing volatility. For example, in 2013, the prices rose by 50% in just 6 weeks. A couple of years later, it rose by 75% in just 3 weeks. So, what's driving this change? And it's very important because the impact of onion price rise is quite grave in India. It can change election results. It can have an effect on other aspects of the society, like increasing the crime rate. And interestingly, if you go into the news media, if you look into the news media, you will see that uh, there are discussions about that, and you can understand certain things which has been well researched and presented in those articles, that why prices are rising, what is imminent, whether the prices are going to rise or fall in the near future, and what events might lead to a change in the future. And we see a repetition of this in many articles. And the question we have to ask is, if we can identify these kind of factors, like causal factors or the factors which follow after we see a sudden rise in the price, can this help in better predicting the price? And also, more importantly, can we understand what are the underlying factors within a time period that led to this change? And we see in the news articles that we get signals, so factors related to the environment, less rainfall or too much rainfall can affect price. Other events such as transportation strike, or other types of costs going up. All these kind of are important factors that lead to a sudden change in the price of onions in India. So, given this background, we would like to understand how we can extract causal relationship from text. So causal inference is an important area of study in many different disciplines. So a lot of researchers spend a lot of time and resources setting up experiments to understand the causal relationship between two events. And when those experiments are done, they record them in different forms of text, including journals and other ways on other medium to disseminate their uh, results. So here the problem is identifying sentences which have causal meaning in it. So not all sentences carry causal uh, semantics, but some do in those articles. For example, the sentence we see on the screen: studies have supported that obesity accelerates AD-related pathophysiology and memory impairment. So we assume that a sentence which has a causal meaning in it has two events present: the cause event and the effect event. And through many different artifacts of the English language, some kind of association is made between the cause event and the effect event, which kind of makes it clear that the first event will have a causal effect on the next event. And that artifact is a connector. So in this example, obesity is the cause event, and AD-related pathophysiology and memory impairment are the effect events. So our task is to identify such sentences and extract such events, which one of them is going to be the causal event and the other is going to be the effect event. So it's not a straightforward task because, as I said, there are thousand different ways to depict causality using the English language. So the easiest is when the causality is present as a marked causality. So the connector, the phrase or the word which means causality is out there. It's very easily visible. But there are many cases where it is not visible. Like in the first example, increased thirst is a symptom of diabetes. Here we can see that diabetes may lead to increased thirst, or other way. But in the second sentence, last week temperature rose significantly. There were several cases of heat stroke reported. So there is an underlying connection between temperature rising and the increased number of heat strokes. But the sentence itself does not have any marker that will establish this connection. Similarly, the same sentence can have multiple cause effect pairs. So we assumed that there is going to be at least one cause effect pair, but it may take many different forms. So one cause might lead to an effect, and that might act as a cause to another effect, like the price of fossil fuels, which was far from the only factor in causing the housing bust that led to the crunch. So price of fossil fuel rose, that led to a housing bust, and the housing bust that led to credit crunch. So things can happen in sequence. On the other hand, the sentence one causal event can cause two effects. And similarly, we might see other patterns like two causal effects might lead to a single effect. And in the same sentence, you have independent pairs of cause effect um, events. And finally, the sentence structure might not always be the same. Like in this example, the illness caused by deficiency of vitamin D is called scurvy. By any standard method, it might seem that illness is the cause here, though it's not untrue, but the actual cause here is, sorry, the actual effect here is scurvy and not just illness. So causal event here is the deficiency of vitamin D, and the effect is scurvy. So, given this background, we decided to use a novel framework to address this problem. So, in terms of as a problem, this is a sequence tagging problem. So, you're given a sentence, the model needs to go through each word and give a tag to it. The tag can be cause, the tag can be effect, or tag can be a connecting connector, or tag can be irrelevant, which means that this word has no important role to play in this sentence. To do this, we designed a reinforcement learning setup. So like any real reinforcement learning setup, there is an agent who tries to move through an environment using a set of predetermined actions. And through these actions, the agent moves from one state to another. The agent is currently in one particular state, and the action will determine which next state the agent will be in. And in the process, every action is associated with a reward. The agent's job is to browse through this environment, reach to a terminating state, reach to a goal, while maximizing the reward. So in our case, the agent is a classification model. In this case, we used an LSTM model with Albert embeddings as inputs. So the action is every word, the agent or the classifier will map that into one of four categories, one of four tags: cause, effect, the connector or the relationship, or none. None means that word is not important. And through this, the agent will browse through the environment, moving from one state to another. So the agent will the state is defined by the current position of the agent, what was the previous states of the agent as well. And in the process, the reward collected by the agent is the improvement in the prediction score. So the current state says the prediction accuracy is this, and the next state, the prediction accuracy was a new value. The difference is the reward. So the agent will try to maximize the reward, or in other words, try to improve the accuracy. So here's a summary of the reinforcement learning setup we used in this case. So we picked up a random subsample of sentences, and at every step, the agent or the classification model will go to a new state, We'll have an input state, the current state, we'll perform an action, and we'll go to a new state. And the state contains information about where the agent is, the tag of the current word, the tag of the previous words in the sentence to get the context. And the reward is defined by the difference in the prediction accuracy through this state transition. So we used some standard data sets like SEMEVAL and ADA, which has a collection of sentences with causal meaning in it. And in addition, we collected our own data set from abstracts, journal papers published in indexed by the PubMed database. And we collected 18,000 abstracts and annotated 1,000 sentences from there, which had causal meaning in it. So we compared a performance with several baseline models, like rule-based model, a pure LSTM, and a pure bi-LSTM model. And with that, we compared our approach, our reinforcement learning-based approach, and we see a remarkable improvement in performance through our model. We also did evaluated this model using an indirect method. So we tried to see whether our model of identifying causal sentences and the corresponding entities, can that improve question answering? So given a sentence like studies show obesity causes memory impairment, we tried to frame causal questions and see how this model can help in answering those questions. So if we used a pair, like a correct pair and an incorrect pair. So we trained the model in a way that if the pair is correct, it will have a high confidence through the question answering model. But if we give a negative example, an incorrect pair, like in this case, studies do not cause obesity, but obesity causes memory impairment, it will have a low confidence score. So we tested this on a subset of 1,000 sentences from our data sets, and we could observe that our model could correctly identify or correctly answer the questions with a precision of 0.916. And we also performed additional experiments using a publicly available question answering data set from Yahoo Answers. We identified causal questions from that data set, and using a 2,000 sentence, creating a 2,000 sentence data set for this task, we could identify that our model could identify the correct causal phrase with a precision of 0.864. And when the causal pair was correctly identified in 98% of the cases, the effect phrase was correct. So from there, we moved on that, like, what is present in those sentences? What actually causes causality, in the sense that what words or phrases or what aspects of the natural language text implies causality? For that, we used the concept of saliency map, which has been extensively used in the area of computer vision to identify important pixels. But we used a similar concept, saliency map, to identify the important words in the sentence. So for this, we used another data set called CausNet, which is created from Wikipedia and has over 500,000 sentences marked as causal sentences. So we built a separate classifier for this task, and which will predict whether a sentence is causal or not. Then we will randomly remove words and see the drop in the probability score. If the drop is high, that means that particular word is very important in determining whether the sentence is causal or not. So we ran this to a bunch of sentences, and here you can see that, like for in this example, discharge, removing the word discharge made a huge difference in the probability score. So using these maps, we try to get an idea what words are important in the sentence, in the sense that what words actually depict causality strongly in the sentence. And our results, our observations are that causal phrases causal and effect phrases are important. Connectors are also very important. And more than one causal phrase can be important. So in the sense that the model is greedy in identifying this kind of words. Our current focus now is identifying the causal distance. Like if there is a causal pair, how can we determine the strength of the relationship? using linguistic cues like likely, definitely. If I say this will definitely cause that, which has a stronger sense than this may likely cause that, which has a weaker sense. So using this kind of linguistic cues and the frequency of a finding, frequency of a causal relationship from the data set, can we identify a causal distance between a pair of events that might help us to identify the strength of the relationship. At the same time, we can explore the dynamism. So causal relationships, established causal relationships might change over time with new evidence. What was thought to be causal may not be causal, or some new confounding variables might have been found that defines this relationship. So this will help us to not only qualitatively but quantitatively define the quality, the strength of the relationship. So with newer evidence, the distance might change. So the distance will have range from -1 to +1. And +1 means it's a very strong relationship. -1 means it's a very strong negative relationships. And 0 will mean that it is a neutral relationship. There are no causal relationship between this pair. So this is, I'll conclude the talk by acknowledging National Science Foundation for supporting this work under the grant number 1948322. And I would also like to acknowledge my research team, who has been working very hard in working this very interesting and hard problem. Thank you.